Thanks everyone for coming this morning and giving up your time to come and listen to Chris Harris. I'm going to do a quick intro of Chris and then hand over to him and let him give us our presentation. Chris is the recently retired Philipson Stowe Professor of Mineralogy and Geology at the University of Cape Town, Geological Sciences Department as it's known today. Chris was brought up in Cumbria in the UK and completed a Doctor of Philosophy and Geology at Oxford University in 1982. And he has been at the University of Cape Town, Department of Geochemistry and then Geological Sciences since 1984. His main interest and research activities have been related to the application of stable isotopes in igneous petrology, hydrology, and economic geology. And Chris today still runs a very successful stable isotope laboratory, hence this work that he's going to talk about. He's a top guy. He's done some wonderful research and work along the way. He's also, as Chris does, produced some really excellent young students. And I think one of them, is a co-author today. Unfortunately, he's in the States doing a PhD. So he won't be with us, but Chris, over to you, and thanks for your time.
Morning, everybody. It's a pleasure to be here. Thanks for your hospitality and breakfast. I'm not an expert on Phalaborwa. I went there once for a few days with my students and carted a whole lot of rock back to UCT, and I've become an expert analysing stuff and looking at the geochemistry. So I just want to explain a bit. Joshua Munro is my student. And this project came about because he did his degree in WITS, wanted to do honours at UCT, and he wanted to do a project in igneous geochemistry. So he came to see us in 2020 to do it in 2021. And as I'm sure you remember, that was the COVID year. And so we had to devise projects where the student never went anywhere near any rocks. And we had a big collection of Phalaborwa rocks in our teaching collection. So I thought, well, why don't we work on those? I knew something about Phalaborwa and was interested. So that's what we did. So Joshua did that. He did his honours. And then we try and design, these days we design honours projects so they can take that work, stay on another year and get a master's out of it. And you're allowed to use the same work. And Joshua finished his master's and handed in, not that around October time. So he was actually registered as a master's student for less than a year. He's now at the University of Texas in Austin doing his PhD. So a lot of this work is his, and I devised the project and set him loose. He was a fantastic student. He got the award from the Society for the best MSc of 2022. So the top line says, understanding oxygen isotopes. I make no apology for being a geochemist and showing you nasty geochemical slides, but just to make sure that people have a vague idea of why we do this and what it means. Okay, so measuring the oxygen isotope ratio in substances, obviously in Phalaborwa in this case. The ratios we measure will be 18.0 to 16.0, but the numbers are not convenient to deal with. So way back in the 1950s, a notation was devised which is delta notation. And basically we define delta 18.0 as 1,000 times the ratio in sample divided by something we used to compare it with and multiplied by 1,000. And the comparison material is seawater, which is, geochemists use a lot of horrible acronyms. SMO stands for Standard Mean Ocean Water. It's not just any seawater. It was collected by some people in the 1950s. They collected a large volume, it all disappeared not that long afterwards. And I think we're on SMO number 4 or 5 by now. So that is what things are compared with. All you need to really remember is anything with a delta 18.0 value that's positive, greater than 0, has more 18.0 than seawater. Anything with a negative delta 18.0 value has less 18.0 than seawater. So on the graph here, and apologize to the people listening remotely, I'm going to go over the points. So 0 is there, seawater is there, it's being compared to itself, so by definition it will have a delta rating of 0. Okay, and then we have the Earth's mantle, which is higher, it's about 5, 0.0 per mil. You make a magma out of it by partial melting, mid-ocean basalt. That's a little bit higher, 5.7. Sedimentary rocks, crust is all over there, and the only reservoir on Earth with negative delta 80 value is rainwater. Okay, that's labeled as meteoric water. Always confuses students. They think that meteoric water comes out of meteorites. It doesn't. Meteorites are rocks that fall out of the sky. Meteoric water is water that falls out of the sky, i.e. rain, snow, precipitation of any type. And the reason that sedimentary rocks are over there is because they exchange with meteoric water. It looks totally counterintuitive because you think that if you have things down here reacting with things over there, it would all be dragged that way. But it doesn't work like that. That is because there's a very big isotope fractionation between minerals and water at low temperature. It's about 30 per mil, so if you have a rock fully weighted with the water there, the rock will end up right over there. So the crust is here at high values, mantle is there. So it's a very useful tool if you want to know something about the Earth's mantle. And as geochemists, that's one of the things we're really interested in. That if you have continental crust contaminating magnets in the mantle, it raises the delta 80 value. If you have subduction of material that's seen the surface, then you will also see higher delta 80 values. And for many years, until the 1990s, people thought that the mantle showed very little variation. Indeed, and it's become more and more obvious that the mantle is actually quite variable for oxygen isotopes. It's much more variable for other things, but oxygen is a major element. It diffuses quite fast. So at the high temperature of the mantle, you'd expect everything to diffuse to a constant value. It hasn't done. There are some variations. Okay, just a little bit about radiogenic isotopes, and I'm going to talk about strontium and neodymium a little bit here. And they are radiogenic because they're produced by radioactive decay. Okay, oxygen isotopes are not produced by any decay. Once they're there, they stay there. The only way of changing their values is to add something else. Okay, these things, on the other hand, although the isotopes we measure are stable, strontium 87 and 86 are stable isotopes, but they're produced by radioactive decay, so we classify them as radiogenic. Okay, so rubidium 87 decays to strontium 87 to increase the strontium 87 to strontium 86 ratio, and in the neodymium system, 147 samarium decays to 143 neodymium. You may not have heard of the elements themselves, but they belong to the rare earth group of elements that are becoming increasingly important in high-tech electronic aspects. So they're important elements. And the two things that behave rather differently, rubidium decays to strontium. The parent is more incompatible, doesn't like to go into minerals, it goes into magmas that are being produced. For strontium, for neodymium, it's the other way around. The end result of all you really need to remember is if you plot one against the other, traditionally neodymium is on the y-axis, strontium is on the x-axis. The Earth's mantle is up here, crust is down there. There's nothing in that quadrant, nothing in that quadrant. And then this part is labeled crust. These days, more and more people are recognizing, I've now got a stick, so I can, I'll still have to lean a bit over. Okay, so where it says crust there, you can also have mantle with high rubidium strontium ratio and low samarium neodymium ratio. So that's another way of tracking where magmas come from, what's going on in the Earth's mantle. Okay, that's enough geochemistry. One of the big advantages of oxygen isotopes in geochemical studies is that oxygen is the major element in nearly all rocks. Most rocks are about 50% oxygen, and that means that it's very hard to change the oxygen isotope ratio of anything once it's formed. Other thing it means is that if you have a mixture and you have something halfway between two end members, it's 50% of one, 50% of the other. And that is because the concentration of oxygen is the same in all the end members. This does not apply to things like strontium, neodymium, and lead isotopes that are trace elements that can be in very different proportions. So the mantle delta 80 is around 6, or mantle magmas are around 6. Crust is higher, so it's a very good tracer for what's happening in magmas. The downside is that alteration, it's a low temperature process that affects oxygen isotopes quite considerably. So you have to be really careful to eliminate any effects of alteration. And with something like Phalaborwa that's 2 billion years old, then one has more of a problem than something like Iceland, where you have rocks erupting today. Okay, so just a little bit of detail about mantle magmas. Mid-ocean ridge basalts are on the left, very narrow variation. OIB stands for ocean island basalt. These are other magmas that come out of the mantle unmodified, very narrow range, something like 4.5 per mil to 5.5 per mil, not much variation. The only mantle material with different oxygen isotope ratios that's been known for a long time is eclogite that comes up in xenoliths in places like Roberts Victor. And there it's well known that you can find quite a big variation in delta 18O. More about that a little bit later. How to analyze? We use this piece of equipment. It's got a laser at the left-hand end with a camera. You can see a glow there. That's a mineral that's being zapped by the laser and reacting with fluorine. So oxygen, if you remember your periodic table, is the second most electronegative element. The only more electronegative element is fluorine, which is very nasty. And fluorine is the only thing that will knock oxygen out of minerals. So we do a high temperature reaction using laser power with fluorine-bearing compounds. We don't use fluorine itself because it won't freeze out into liquid nitrogen. So if you have a leak, you're stuck with the fluorine getting out and you just have to run away. We use a compound called chlorine trifluoride, which will freeze into liquid nitrogen. So if it leaks, you just stick it in a big tank of liquid nitrogen and then take it away with you and drive deep into the forest and chuck it out and then run away. So it makes it a little bit safer. But the safety aspects is why people don't do much oxygen isotope analyses, because it's very hard to convince your safety officer that you should have these kinds of things existing in a university building. So it needs a mass spectrometer. We collect the samples and take it to a mass spectrometer. You can also have the mass spectrometer stuck on the end of one of these as an attachment, and it measures the isotope ratio. So for oxygen, we're measuring mass 34, which is an oxygen 18, and the 16 against mass 32, which is 2 oxygen 16s. People also measure oxygen 17, which is very unabundant, and we won't bother talking about that for this talk. So Cape Town to Phalaborwa is about as far as you can drive in South Africa. I think there's not too many places that are further apart than that. We wanted to collect a lot of rocks, so flying is not an option. Beautiful geology that you drive across. Phalaborwa is interesting, not just because of the mineralization and rock types. It also has strange strontium isotope ratios that go from 0.7039 to 0.71 that look crustal. Neodymium's low, also looks crustal, yet the rocks are carbonatites and pyroxenites that ought to be mantle-derived. The other thing is it's the same age as the bushveld. So I'm interested in the bushveld geochemistry. So having something like Phalaborwa that's the same age but very different isotope composition that surely does come from the mantle was a reason for looking at this. The fact we had tons of this stuff in our teaching collection. So this is what the Phalaborwa complex looks like. It's quite a complicated thing. It's not just one pipe. There seem to be various bodies. Lulikop was a hill in 1960, as various people have told me. Now it's a very deep hole where a lot of the material has been removed away. That is carbonatite, which has chalcopyrite mineralization, all kinds of other things. It's surrounded by a whole series of phlogopite-rich rocks, pyroxenites, pegmatite-like things, and it's a multi-commodity mine. I'm sure many people here know much more about Phalaborwa than I do, but they mine a whole bunch of different things. And so there are actually 2 mines on site. One is Phosphor's mine, which is mining largely apatite, but a whole bunch of other stuff as well, and a copper mine, which mines the area around Lulikop, which is the carbonatite. Very complicated cross-section, which either my student or I drew. This comes from work by various people, forgotten whom. And there's a rock type there in green called phosgorite. And this is the type locality of phosgorite named after the Phosgor company. It's an apatite, olivine, pyroxene, various other things. Rocks is a very unusual rock. This is the type locality, but it's been found in a variety of other places since then. It's also the only carbonatite complex to have economic copper deposits. So lots of interest. Around the complex, there are a series of satellite syenite intrusions that we were also interested in. So the things that we did, that's my student Joshua with one of the mine geologists, Megan Sauer. We couldn't go into the pits there because, I mean, I've been given all kinds of excuses by mining companies over the years why you can't take students into pits, they're dangerous and so on. This is the best excuse I ever heard. Apparently there's a buffalo running around that the week before had written off a 4x4. So they said, no, we can't go there. But it doesn't matter because there's huge piles of stuff that they've thrown out from the development of the pit. It's beautifully fresh despite its age, and they had kilometers of core in their core shed, covered by centimeters of dust, because not many people have been there recently, with baboons jumping around on the roof of this thing. But we were able to go through their core collection. We particularly wanted cores that went through the contact between the pyroxenite and the intrusion and the country rock, to see what effect the country rock had on the intrusion. And then we drove around sampling country rock, which are gneisses, very old gneisses in that area, and schists and all kinds of rather altered and not very well exposed rock. This is what it looks like on Google Earth with Luley Cockpit. That's the dark thing in the middle. You can see the rock slide on the north side going into the pit. Various slimes down in the south, and the Kruger Park is just over there on the right. I gave this talk somewhere else, and people were the most questions they had about how much of the contaminated water got into the Kruger Park and poisoned the animals. That's what they were interested. Probably not much, because I did actually do a hydro survey in this area many years ago with Nick Stephen and others. So that's what it looks like. This is Luley Cockpit. It was once a cop. Now it's apparently the deepest hole, widest hole in South Africa. It's now mined underground. That's what some of the mineralization looks like in one of our samples in our teaching collection, I think.
So just how deep was that?
It's about 500 or 600 meters, I think.
1.5
It's 1.5 kilometers across.
kilometer.
Yeah. It says something deep, but talking John Bristow is, and I don't want to touch it because we might have another catastrophe. So there's lots of really coarse, really fresh rocks containing apatite. Phlogopite is a pegmatoid rather than pegmatite because it's not granitic in composition. Giant dioxides, lots of student collections and collections in geology departments have these really big pyroxenes in them, and they all seem to come from Phalaborwa, bigger than my hammer there. The carbonatite's difficult to access because it's underground. We didn't want to go underground because it was not that long after COVID. So the last thing we wanted to do was to go underground, catch COVID again. But there's lots of stringer veins of the carbonatite coming out into the country rock. And that's a magnetite stockpile, the top right. I think they were saving it for a rainy day. I think they now got rid of most of it because the price has gone up, but that's all dug out of the hole. Beautiful, quite, that concentrate is quite pure magnetite. Just some more detailed pictures. This is where the buffalo lives, so they wouldn't let us go down here. They're also, they told us about lion kill and other things that are happening. This is Megan, was brought up and lived in Phalaborwa, now works for the company. She's a UJ student, did a master's on it, and she very generously showed us around. Any kind of mine visit, if you don't have the buy-in of and interest of the people involved, it often doesn't work very well. So we're really grateful to her for unselfishly giving up her time. And also, she was also doing masters on Phalaborwa, so we were sort of treading on her territory, but she was very happy to help. Giant crystals of phlogopite, diopside, not much olivine. The phosphorite is nearly all mined out. There's hardly any phosphorite around. We have to search around boulders to try and find some. These are some of the veins of the carbonatite that infiltrate. The sort of more goldeny green is the pyroxene. I think the other grayer green is apatite and other things. But wonderful mineralogy, beautifully fresh, considering how old it is. And presumably that is related to the level of erosion. You know, this stuff was buried deep below the surface until relatively recently in geological time. The last 25 million years has seen the uplift and erosion down. So in common with the Bushveld, Friedewald, and other rocks in South Africa, they're very old, but they are wonderfully well preserved, considering. If you try and find olivine in the Karoo, rocks that are only 180 million years, they're much less fresh, much more altered than these things in the much older rocks. And it also obviously helps that they're digging stuff out from deep down because it's protected from weathering. So fantastic place to visit. These are the cyanide satellite intrusions. There are probably quite a few of those in the distance. You probably can't see on the screen. Some of them might be, copies of gneiss, but most of the gneiss seem to be planed down pretty flat. They extend into the Kruger Park. We didn't go and sample those because trying to get permission to work in the Kruger Park was way too much hassle. But there are plenty around Phalaborwa. This is what they look like, well protected by barbed wire fences. They're made of cyanite. And this is the base of one of these, brecciated. So some people interpret the cyanites as being metasomatic, but based on this and other evidence, we think they're intrusive. These are magmas intrusive, and that's the magma pushing through the surrounding country rock. Interesting wildlife in the area. It's a footprint of something big. This is within the mine property, driving from the mine past the slimes dam. I guess this is one of the culprits there. So I guess you have to be a little bit careful wandering around. There are other interesting minerals. This is bedelliite. Apparently, Phalaborwa has the best largest bedelliite crystals in the world. One of Bruce Cairncross's pictures from a geobulletin relatively recently. Beautiful bedelliite. We also analysed that. The carbonatite itself contains very pretty pink translucent zircon crystals. Mine geologists all had their own pet specimens, and we couldn't persuade them to either give or sell us their samples. So we didn't have any of that. So this is what we analysed. The pyroxenites are from the outer part. Pegmatites a little bit further in. Carbonatite in the middle with the phosphorite. Cyanite as satellites around the outside. And you can't see it, but that is in order of age. So pyroxenites, pegmatites, carbonatites, phosphorite being the younger. And cyanites, we don't really know the age relationship. Presumably they are younger. And this is what we analysed. In order to get fresh material, the way to do it is to crush the material, separate the minerals out, sieve them, separate, clean them and all of that, and analyse minerals. So he did, Joshua did all of these kinds of things. I think the top left is egerine from the cyanites, alkali feldspar, apatite, which is hard to distinguish from dioxide, but it's a less intense green, calcite, bedelliite, not much of that because the crystals are quite rare, magnetite, olivine. Okay, that is quartz. That's pretty translucent there. That is in the country rock and the cyanites. Phlogopite, vermiculite, that's another thing that they mine there. And orthopyroxene in places. And this is the data that Joshua got. The only previous work, there are a few analyses in a PhD by a lady called Erickson, I think it was Sandra Erickson, from Witz in the 1970s. And then a paper by De Cray et al., which is much more recent, where they analysed appetite for oxygen isotopes using a SIMS machine. SIMS stands for secondary ionisation mass spectrometry. Our machines cost 5 or 6 million. A SIMS machine costs more like 50 million. It takes about 3 people to run it. They go wrong, but they produce data in situ, so they can analyse a spot. So you don't have to go through all the tiresome mineral separation, the stuff that Joshua had to do. That's what PhD students are for, if you're involved in geochemistry. It teaches you a lot about the rocks. You learn to recognise minerals in sitting there rather than having to make thin sections. So key thing here is that the Earth's mantle is a grey strip going there, and nearly all of the Phalaborwa rocks, except magnetite and bedelite, are well to the right of it. They have significantly higher values than the Earth's mantle. Okay, that will suggest either they're crustally contaminated or that they come from a funny mantle that's very different to most mantle and the mantle that's the source of mid-ocean rich basalt. The Cray et al.'s apatite data is all over the place. They had quite a lot that were high, and their apatite is significantly higher than our apatite, and they have some that go to much lower values that we didn't find. Okay, I don't know what the answer is there. I'll show some comments on it in a minute. And when you do this, the best way of representing the data is to plot the delta rating of one mineral against the other. And this tells you whether things are in equilibrium in terms of oxygen isotopes or not. So the top left is phlogopite delta 80 against dioxide. Vast majority of samples in equilibrium. Altered phlogopite samples lie off the equilibrium array. So that's evidence of alteration, but for the most part, there's very limited evidence of alteration. And the slide just summarizes what we think the magma's delta 80 value was based on the mineral data. They're not quite the same because the minerals fractionate the isotopes slightly as they crystallize, but we have magmas that are around 7.3, 8.3, 6.7, 6.12, higher than the mantle, and a little bit varied. The olivine in the that's in the phosphorite, 6.7. Those are the most mantle-like. The pyroxenites somewhat higher. And so the early rocks have a more mantle character, if you want to think of it like that, than the later rocks. These are the carbonatites. I've worked on lots of carbonatites in South Africa and elsewhere. They are invariably very altered, messy rocks to deal with. Phalaborwa is the exception, along with a carbonatite complex called Dicavillum in southern Namibia, which also has very fresh carbonatite. So for comparison, there's some other ones shown there, Spitzkop, Southern African carbonatites, and I've got the Fen, Ochre, Alno complexes there, which are Scandinavian complexes. Phalaborwa is within the red ring, and not much variation, and the values go down to what one thinks, or Peter Dinas thought of being mantle-derived carbonatites. So they look like carbonatites that come out of the Earth's mantle, pretty much unmodified. Rather than rely on carbonates, which are susceptible to low temperature exchange, we separated minerals. So bedelite suggested a magma, so that's bedelite as a crystal in a carbonatite. The magma value is 7.6, magnetite gives 7.8, phlogopite 7.4, so the carbonatite magma was about 7.5-ish, there or thereabouts. Higher than the mantle, but not really that high. On the left is a schematic of a drill core. We have some intersections between the outer pyroxenite and the basement. Basement values are for delta 80 are 9.5, 8.5, that kind of thing, and well away from the complex are similar. The pyroxenite values are the same as the other pyroxenite values in the middle of the complex. So no evidence whatsoever of any interaction between the wall rocks and the complex itself. So it didn't really do much. There wasn't much fluid fluid infiltration from the outside in. It hasn't changed any of the rocks there. We've looked at hydrogen isotopes, which are the diagrams on the right. No evidence for external fluids infiltrating into the intrusion. So it's a magmatic intrusion, hasn't assimilated the wall rock at all. Doesn't mean to say the magma wasn't intruded, containing crust, but there was no wall rock assimilation and no infiltration of rainwater, surface water, etc. at the level that we see it. Of course, we don't know what happened at the original level of Phalaborwa. We don't know if it got to the surface. The original surface is probably several kilometers above what we see now. If you reconstruct the escarpment across, there's probably at least a kilometer or so of material that's been eroded away, possibly the bushveld intrusion as well. We simply don't know. Presumably it erupted, but we don't know. We don't see those materials. Some people think that phosphorite is spelled P-H-O-S. So this is a Williams Jones should know better because he's a South African, originally from the University of Natal, I think now in Canada. They looked at phosphorates around the world, and they like to think that it's carbonatite metasomatism that's producing phosphorite. None of the data that we produce suggests there's any evidence for the carbonatite causing metasomatism. The silicate rocks don't show any alteration. There's no disequilibrium. The carbonatite are a little bit higher than the silicate rocks. There hasn't been any effect there. So we don't think that carbonatite metasomatism is the answer at all. We think this comes out of the mantle, and it's mantle derived. I should just go back a little bit to this slide. I haven't got, maybe it's later. Okay, so Decray et al. Also found that the cyanides had apatite with low delta rating. You can see them on the left-hand diagram. It goes to what they say is trachyte is cyanide really, and the cyanides have low delta ATNO values. We didn't find this at all. All the cyanides are pretty much the same. We analysed egerine and the apatite. So no evidence for magmas with low delta ATNO, which will be an indication of interaction with surrounding surface water. So we don't see that. No evidence of phenetization, really. This just summarizes the values that we have. On the left of the actual mineral data. It's been recalculated as the magma values on the right. The grey line that goes through all three histograms is mid-ocean ridge basalt. That will be pure mantle. All of the Phalaborwa rocks are well to the right. Okay, so they all have higher delta ATNO values than mid-ocean ridge basalt. The country rock, we analysed lots of country rock. The average delta ATNO is 9 per mil. So if you try and mix country rock with mantle-derived magma to make these compositions in the middle, you have to have an enormous amount, 50% or so, of country rock. So they wouldn't look like carbonatites, they wouldn't look like pyroxenites, etc., if that model worked. You'd have so much contamination that you would fundamentally change the composition of the magmas that it wouldn't look anything like what we see in Phalaborwa. So our conclusion is that you can't do it by crustal contamination, and there's no rock beneath that level that's going to have a higher delta ATNO. These are high-grade metamorphic rocks that represent the basement in that part of the world. We know that from looking at the Friedewold structure. They're very similar in composition to Friedewold basement rocks. So crustal contamination is not an option. Apatite's an interesting mineral. It's for many years it's been known that it's problematic for oxidant isotopes. There are three methods. One is the same method that we use. One is the Sims method that Decray et al. Used. And there's a method that the paleo environment people use where they convert to silver phosphate and analyze the silver phosphate. That eliminates the water that's present. Our method by laser fluorination takes all the oxygen in the mineral into account. And this was a study, an international study by 3 different methods to see why, if we could work out do the different methods give different values, and we found out that they do, and why that is, and we didn't find out why it is, but it just so happened that the overall standard that we use for this is something called SARM32, which is run-of-mine Phalaborwa appetite. So I got quite interested. That's what the first reason I got interested in Phalaborwa was, why are these foreigners analyzing all of our standards, and we should be doing it ourselves. So I started doing it, and then I wanted to see, is the mine stuff different to the overall appetite? And in this study, we got the same values as other people, slightly higher, but not much. De Crea and L got, on average, much higher values. So I suspect that there's some issue with the SIMS method that doesn't give us good data as the other two methods, laser fluorination and phosphate method. But that's an ongoing piece of work. And not quite sure what the title of this was, but it was something about overall summary of what's happening. Fractional crystallization is not a way to change oxygen isotope ratios because it's a high temperature process. Crustal contamination doesn't work because the contaminants don't have very high delta 18O, so you can't make a high delta 18O magma in Phalaborwa by assimilation because it just don't have high delta 18O crust. You need 55% contamination by average country rock of 9 per mil, and 55% country rock plus Phalaborwa magma is going to give you something that's, I don't know, diorite or something. Won't look anything like what we see now. So the conclusion is number 3, which is it must be mantled with a high delta 18O value. And that would mean that the high strontium and low neodymium that you see is also a mantle thing. So it's indicative of a weird mantle in that area that was around at the time. Okay, that's interesting of its own, but it's also interesting that this is the same age as the Bushveld. Bushveld is slightly younger, but that might be something to do with the method and things like that. And the Bushveld also has negative epsilon neodymium and quite high strontium isotope ratio, and it also has high delta 18O values. And so 20 years ago, I wrote a paper interpreting the high delta 18O values as due to crustal contamination. Now I think it's because the Bushveld, along with Phalaborwa, comes out of some strange mantle that was under there. And so it's not just a small volume thing in Phalaborwa, it may well be a much larger volume that made the Bushveld. This is that original work, well, 2005 work done on the Bushveld. Similar kind of diagram, the right-hand one where the spots are in black. That's the reconstructed magma delta 18O value. There's a dashed line showing the mantle. Everything is over to the right, coming from a high delta 18O magma, which we thought at the time was crustal contamination. And one is allowed to change one's mind in science. And so now I think it's perhaps due to strange mantle in the area. When I first came to South Africa, it was to work on Karoo volcanic rocks in Antarctica. That's where I first met John Bristow a long time ago. And I've been analysing Karoo rocks ever since. And the picrites in the Karoo, this is another rock collection exercise where a lot of the stuff was collected by John and others. We separated olivine, we analysed it. The Karoo picrites, which are the most primitive mantle-derived magmas, all have high delta 18O as well. Okay, so it's a bit of a coincidence that we have the Bushveld, we have Phalaborwa, and the Karoo with high delta 18O, and we're trying to explain it by crustal contamination. They're in pretty much the same place. It may represent quite a big, long-lived, anomalous mantle sitting under there. How do you get strange delta 18O values in the mantle? The only sensible answer is by subduction. We have samples of such material at the surface because they come up as eclogite xenoliths in kimberlite pipes, Robert Victor being the best example. So we spent lots of time, and I've had other students, Bogdan and Radu, did a very nice study on this. And it's one of these plots where you plot delta 18O value of one mineral, it's garnet, corundum, kyanite, against clinopyroxene. They're all in equilibrium. They're not affected by any exchange. It's the values they had as they came out of the mantle. Quite a big variation, and it actually doesn't go to high values very much. It goes to much lower values. Okay, and this is most people think that this material was once ocean crust that's been subducted maybe as long as 2 billion years ago, maybe longer than that. And on the right is what you see if you do a oxygen isotope cross-section through an ophiolite, which is abducted ocean crust. And near this is Somalia in the United Arab Emirates. Near the top, you have high values where you have low temperature alteration by seawater. It gradually goes down and it reaches a minimum at something like 4 or 5 kilometers. Then it comes back towards the value that it started with as mid-ocean ridge basalt. And so low delta 18 eclogites, like the one on the left, would be sourced from somewhere over there. It's just that we don't see the high delta 18 eclogites at Roberts Victor. After all, Roberts Victor is just one place. It's 750 kilometers from Phalaborwa. We have no idea if it's representative of what's been subducted and what is left down there. So, if you have low delta 18 eclogites, then by mass balance, with reference to the diagram on the right, then we must have high delta 18 eclogites somewhere. This is an interesting diagram because the dashed line on here and the solid line, they're very close together. The solid line is the integrated, the solid line is the starting composition mid-ocean ridge basalt. The dashed line is the integrated delta 18 of all of that crust, and they're very similar. Okay, that's either an extraordinary coincidence, or what it actually probably means is that exchange of seawater with mid-ocean ridge basalt is buffering the delta 18 of seawater, so these values stayed the same for the last probably 2 billion years. We know that Archean seawater was much hotter and had a different delta 18O. It's hard to resolve which is the most important effect. But for at least 1 billion years, seawater stayed the same delta 18O by being buffered by this exchange. And so some of this material gets down into the mantle, and if it's lucky enough, it comes up to the surface or ends up being partially melted to make some kind of igneous body like Phalaborwa or bushflat. So this is just a few conclusions. The high delta 18O values at Phalaborwa do represent those of the magmas. Wasn't caused by crustal contamination or alteration. The cyanide intrusions, they're not metasomatic. We think they're caused by partial melting of the surrounding metasomatized basement. There's a strong similarity with the bushveld here, which is the same age, and also the much younger Peru material that suggests that this abnormal mantle sat there for 2 billion years and is, comparatively recently geologically has been remelted and has ended up in magmas at the surface. And the high delta 18O values and the metasomatism that we see in some of these areas doesn't have to be related. The delta 18O values come from the bulk rock, the metasomatism. It's fluids passing through this area by various events of partial melting, et cetera, et cetera. So they don't have to be related. But the delta 18O values, I think, it's all some big subducted thing that's been sitting there for a long time. Thank you for your attention.
Thank you. Okay, thanks, Chris. Sorry about the little glitches, but I'm sure Chris is also, ready for questions, and we can have some discussions. I'm also going to try and just get rid of this presentation.
While we wait, Julian wants to know.
Again, Henny?
Lithosphere, mantle lithosphere. Gillian,
Carry on.
You want to put your question, Gillian?
Thank you for that fascinating talk. It so happens that I'm kind of dipping my toes in the water and looking at oxygen isotopes in flood basalts at the moment. So do you have any handle on whether your mantle is lithosphere or cenosphere?
if you count blobs of eclogite sitting down there as lithosphere, then it's lithosphere. But of course, they could be sitting beneath that at some stage, rising up towards the lithosphere. We don't know. So yeah, lithosphere. I mean, it's not asthenosphere in a geochemical sense. It doesn't look anything like more in all the isotope systems.
Well, of course, the
And-
asthenosphere could have more in it than just a morb source.
Yeah, well, there could be a plume source under there. I guess you don't believe in plumes, so then it isn't going to be a plume source. But some people might think there's a plume source under the depleted asthenosphere.
Just to clarify, my position is not that I don't believe in them. I'm not a religious person. I think the surface observations that we can make do not require them. That's my position, but I don't want to talk about that. Okay, so I'm just looking for a graph I drew, which summarizes some oxygen isotope ratios for various flood basalts, but I'll let somebody else question you while I search around for that.
Well,
Thank you for your answer.
Look forward to seeing that.
Well, I mean, we got to also go back to sort of mantle metasomatism, and maybe Steve and Russell can come in there, particularly from a point of view of those interesting Karoo rocks in the Lubombo right next door in Kruger Park.
An ignorant miner has asked, can you please explain the high copper content?
Yeah, well, it was going to be my
Mantle
question.
copper. It doesn't come from the country rock. It doesn't come from contamination. It doesn't come from hydrothermal system. And it's probably copper that comes out of the mantle.
And I mean, can you see the signature of can you do an analysis on the copper?
You could do copper isotopes, I guess, but the total variation in copper isotopes is not that much. And I suspect you'd end up with a fairly ambiguous answer. It's like sulfur. You can do sulfur isotopes and stuff. And the problem is you end up in the middle with a mantle value that could simply mean you've got a mixture of sulfate, original sulfate, and sulfide.
Yeah.
So we could probably get it done. We don't do copper isotopes ourselves. Could be done.
And that fluid system, would that go with I mean, you said it, that's the only copper rich, and it really is rich carbonatite that we know of effect.
The problem, you can have a fluid transporting things around, but it would take the copper out of, might take mantle copper, put it somewhere else, and it will still precipitate with a mantle copper isotope ratio because there's no copper in water. So unless you fractionate it somehow, lose half the copper in some other form, it's not going to make a big difference.
But because it is this amazing anomaly that's got all sorts of everything in one spot.
Yeah,
in big
and
concentration.
that can be extended to isotopes.
Just can I just ask the original location of the Phalaborwa deposit, sitting more or less on the edge of the Carpal Dot and up against the Zimbabwe mobile belt. Could that have something to do with the isotope?
Short answer is I have no idea. I haven't even thought about it. It's a very good question. Might have something to do with the plumbing system. I don't know.
Is it similar work being done in Phalaborwa?
There is. Phalaborwa is. I did once ask Grant Cawthorne, why don't we do a stabilized study of Phalaborwa? And I looked at the rocks. They're horrible. They're all altered. They're very, very altered compared to Phalaborwa. I guess it doesn't have carbonatites. It doesn't have, they're mostly fairly felsic, undersaturated, and some saturated rocks. But they weren't really amenable to this kind of study because I get, if somebody mined it down to a big hole in the ground, then it might be worth doing. But hopefully nobody's ever going to do that. Not that there's anything valuable, I don't think, in Phalaborwa. But I did look at the rocks and decided no.
Yeah. Steve Haggerty, have you got a comment?
Yeah, hi, Chris. Great
Hi,
talk.
Steve. How's it going?
Good, thank you. You showed a diagram, but I couldn't quite read the ordinate or the abscissa of carbon versus oxygen.
Yes.
Would you comment on that? Does carbon support your oxygen isotope interpretation?
The carbon, it's okay. So you're familiar with Peter Dynas's mantle box for carbonatites. Most of the Phalaborwa rocks sit in the middle and then they extend over towards the higher delta 18O, but keep the same carbon isotope ratio. So it's entirely consistent with original mantle carbonate that has suffered a degree of low temperature alteration, which has affected oxygen, but not carbon, because there's oxygen in water, but no carbon in water.
But there's carbon dioxide.
Yeah, but it's not, water is, I don't know what percent, 88% of water, whereas it's got a little bit of dissolved carbon in. So it doesn't make, a bit of fluid is not going to make much difference to carbon isotopes, what will make a big difference to oxygen. So, and it's why we took the silicates out, analyzed those to get the delta 18O. The silicate minerals are just so much more, and oxide in the case of bedelite, so much more robust.
I mean, apart from copper, there's this overwhelmingly large and enriched zirconium. So where the hell does that come from?
Well, the mantle, I suppose.
Well, I mean, there's
I can't think of anywhere else where it could come from.
There are a whole host of large iron lithophile, similar to lindseyite, mathiasite, and those exotic mantle minerals, but they're in ore deposit concentrations, as is the copper. So yeah, it's an exceptional and unusual mantle anomaly, is what you're calling upon. So
well, it's an exceptional and unusual intrusion.
right.
So it demands an unusual sort.
But the other comment to make is that it's a large igneous province, and large igneous provinces are typically associated with plumes. And if they're plumes, then the source material is much deeper than the upper mantle.
Phalaborwa itself is not a large igneous province. Bushveld.
No, I took the whole provinces.
Obviously is. So, I mean, if you believe in plumes, then there could be.
It's not a case of believing, it's a case of what is the alternative.
Yeah.
I know Gillian has an alternative, but not for the exotic elements that you're now talking about.
Well, that's right. So mantle lithosphere, stuff that's, been there a long time, has concentrated unusual elements in it, then gets melted and taken to the surface.
Right. Okay.
I was going to ask, well, how does this work, Joel, with Gillian's? How does it support it? Is it or is it conflicting with it? Where do we stand with the two?
Okay, we'll ask Gillian or Jim to comment. Jim Natlin's also on. Gillian, are you there?
Yes, I'm here, and I'm greatly enjoying hearing a toing and froing about whether plumes are required by this from people other than myself. But Jim is, of course, much more qualified than I am to talk about the mineralogy and geochemistry, so I'll pass over to him.
Can you hear me?
Yeah. Speak up.
I'll try. These are old rocks, and whether there were plumes back then, and whether they influenced magmatism in this part of Africa, well, that's an open question. I tend to think of modern instances of whether there are plumes, and I'm very skeptical in most cases. If I apply that experience to something as old as this, I'd say, look for sources in the shallower mantle. It's just a dictum I have, in a way, that look for eliminate the effect of crustal processes, shallow differentiation, whatever, as best you can. And these are such peculiar rocks dealing with
You
some
there?
plume to them right off the top of my head. That's all.
Yeah, very, yeah, okay. Your
My internet
comment.
connection is unstable, it says.
Yeah. Small degrees of partial melts as well.
I mean, the other thing that people have suggested is you have unusual surface rocks that might have interacted with the intrusion. I mean, people talk about simulation of evaporites and things like that. But it's not the case in this because those kinds of surface rocks have been well separated from what we see in Phalaborwa now by kilometers. There's been kilometers of erosion in that area since it was intruded.
Yeah. And just the more you look at Phalaborwa and the more you study it, I mean, it looks like it's exotic, but it's the cohesive type of body.
That's what I think.
Yeah. Okay, any last questions? But thanks, that was fantastic, and we'll get some more discussion going on the emails and so on. Thanks for your time, Chris.
Okay, Julian, if you want to send a diagram
you
with
hear
the
me
oxygen
again?
isotopes, I'd be very interested in looking at it.
Well, if John will permit sharing, I could show it to you because I've managed to find it. So I'd be very happy to get the comments of this knowledgeable group on my pathetic geophysicist's efforts to collate oxygen isotope
Go
ratios.
for it. You can share from there, I presume.
Oh, it looks as though perhaps I can. Yes. Okay. So as I say, I'm just a humble geophysicist. So
Never heard that before.
so I threw together as many oxygen isotope ratio measurements I could find in a very quick literature review of the the red is Iceland, which of course I'm interested in. So this is 0 down here and 10 here for delta 18 oxygen. So 6 is this level here. And I got roughly 6 and 6 and 6 from different Karoo publications. Euler's measurements for average morb, Baikal, EM2, Emisham in China, and so forth. And these are the Iceland ones. So in Iceland, we see, some central volcanoes. This is this and this and this are all central volcanoes, and these are central volcanoes. And this is Iceland rhyolites. So I'm particularly interested in seeing how closely Icelandic basalts resemble continental large igneous provinces.
My first comment will be, are these whole rock data or mineral data or both?
I would have to go back because it's a while since I did that.
And Iceland is unusual because it has the rainwater is quite low, delta 18O. So any interaction of the surface water with the rocks has a much bigger effect in Iceland than it would ever have had in the Karoo, which when the Karoo was extruded was relatively near the equator. So Iceland has like Skaregard and other 55 million year old intrusions, is the effect of a little bit of alteration is much more evident.
So you're saying that would tend to disproportionately depress delta 18?
Yes.
Right. Okay. So we could consider that the real comparable level might be somewhat higher than the red dots indicate.
Possibly. I mean, yes. I mean, I've done a lot of analyses of Iceland rocks recently, and they mostly are sitting the same as morb. They're not all that different. There are some felsic volcanics that are lower, and I think we analysed the highest delta 18O rock in Iceland. There's a paper by an Uppsala student called the highest delta 18O rock in Iceland, which was some low temperature alteration and then really low temperature alteration and assimilation.
Okay, so
sedimentary material.
this was kind of me throwing together a rough collection of the lowest hanging fruit. It's not a
Yeah,
full review, but it would certainly be interesting to work a proper review up, perhaps with the help of a student, master's student could do that.
one of yours maybe. I don't know about that. I'm not sure that ours would.
Well, why not?
Um,
We've got to find some and get
Yeah.
Chris working. at the
Joshua
moment.
Munro would have done it.
Anyway, I mean, clearly there's lots of room for further discussion. I mean, we've now heard Chris's side. We need to hear your side, Gillian. And, you know, maybe something to pick up again on the emails and then perhaps in August.
May I ask how these compare to modern or more recent carbonatites?
You got any data?
Lots of data.
Okay, Chris says he's got lots of data, Jim, so
Unpublished stuff,
I'll
yeah.
connect you on the email and we can kick it around.
I like that comment about
All right, thank you.
look for the hypothesis of least astonishment.
Okay, all right. Thanks, everyone. It's been a great show. Thanks for joining. So thanks, everyone. Thanks, Henny, for supporting, and thanks, Chris, for coming.
My pleasure. Thank you for
Okay, and thanks
joining.
to the audience.
and the audience.